we saw very quickly how to add halogens to the ring. We added a nitro group, we added a sulfonic acid group, that SO3H. What if we want to add an alkyl group? If I have a way to easily form an alkyl carbocation, turns out that that is a strong enough electrophile in order to react with a aromatic ring. So alkyl carbocations are produced from an alkyl halide with AlCl3. We used iron, right? We used an iron halide to add a bromine or a chlorine. Now we're going to use an aluminum halide in order to generate the carbocation that we need. So let's start with this reaction. It's called the Friedel-Crafts alkylation. I start with an alkyl halide. Here's our RCl. Chlorine is the most commonly used one. We might as well just call it the chloride because the chlorine never gets introduced into the molecule, into our product. So just use an alkyl chloride with AlCl3. Very similar thing happens with this, like what happened before with the halide. If I have something like CH3Cl and I react that with AlCl3, we've got that same sort of reaction where we get CH3 plus, we have a carbocation, and AlCl4 minus. So it's this ion pair, really, that is the reactive intermediate. But the aromatic ring attacks the carbocation, regular old carbocation, just like we've seen before. That makes the new bond to the ring. Still have that same hydrogen on there, which will then get removed by AlCl4 minus this time to restore aromaticity. But really exact same mechanism as we saw before. This is very helpful if we want to add a simple alkyl group, but if we try to get fancy with it, we're going to have some problems. So there are some real serious limitations of the Friedel-Crafts alkylation, which you are responsible for knowing. If you propose a Friedel-Crafts alkylation which will not work, you will not get credit for it, at least not get full credit for it. Only an alkyl halide can be used to make the electrophile. So that chlorine has to be on an sp3 carbon to do this alkylation, like we talked about. That means a vinyl halide will not work. Chlorine cannot be on a double bond. An aryl halide will not work. The chlorine cannot be on an aromatic ring. Okay? An alkyl halide is what we need. If we have a strong electron withdrawing group on the ring, that will deactivate the ring towards any alkylation. So if I have some sort of group that's pulling electron density out of the ring, the aromatic ring is now not nucleophilic enough. It doesn't have enough electron density to go out and attack the electrophile. So electron withdrawing groups, we'll get to those in a moment. For now, let's consider anything with a plus charge right by the ring. So an ammonium group, a nitro group, which has a plus and a minus in it. Cyanide, right, that cyano group. Anything with a double bond O directly next to the ring, like all of those have. Those are all electron withdrawing groups, and all of those will deactivate the ring towards alkylation. So we'll reinforce that a little bit later when I talk more about those deactivating groups. The other problem, it's very difficult to stop the reaction after a single substitution. In order to get a monoalkylation product, a very high excess of benzene must be used. So if I used 1 mole of benzene and 1 mole of alkyl chloride, in this case T-butyl chloride, we'll get unreacted benzene, we'll get a little bit of monosubstituted, but a lot of disubstituted. That's because as soon as one substitution happens, then this is now more reactive than the original benzenes were. So this will react faster. So we'll get disubstitutions happening quite a bit, and then we'll end up using up our alkyl chloride and have benzene left over. The solution to this is have a huge excess of benzene. So benzene, huge excess. So 10 to 1, 20 to 1, 50 to 1, whatever. The better excess you get, the better selectivity of your product. Huge excess, limiting reactant then being the T-butyl chloride with AlCl3 catalyst. That's our limiting reactant. Then our major product will be monoalkylation. So there's our T-butylbenzene as the major product. Okay. So a lot of times it can sort of be understood that we'll have a monoalkylation product, but in case you're asked about it, okay, if you want to just do one alkylation, you need to have a large excess of benzene. So I do an alkylation. This is more reactive, but I've still got a billion more benzene molecules that are able and willing to react. So what else? Here's the big limitation for Friedel-Crafts alkylation. Since it's a carbocation, since it's a regular plain old alkyl carbocation that we've formed, those carbocations are subject to the same sort of rearrangements that we've seen carbocations do before. So if it's a primary carbocation, it will almost undoubtedly and reliably pretty much do some type of rearrangement even before the substitution happens. So if I have a primary carbocation next to a secondary or tertiary carbon, it'll undergo a hydride shift. So just remind ourselves what that is. If I have N-butyl chloride and react that with AlCl3, we'll get this N-butyl carbocation that is primary, but that won't be around for long. We'll have a hydride shift. Very quickly, one of the hydrogens from the secondary carbon next to it, its electrons will allow it to become attached to that end carbon, and what we'll end up with is a secondary carbocation right there. So that's the sec-butyl carbocation. That'll be the major product if you were trying to have one chlorobutane. You'll end up with your 4 carbons attached at the second carbon instead of the first one. So that's a primary carbocation next to a secondary. If that were tertiary, that would be even more reliable if I had a methyl group there, for instance. If I have a primary carbocation next to a quaternary carbon, then we'll have an alkyl shift. So here is a T-butyl group with a CH2 and a Cl. It's called neopentyl. So there's neopentyl chloride. It's 5 carbons with 3 methyl groups on the end. So 3 methyl groups, a quaternary carbon, a CH2, and a Cl. AlCl3. We end up with the very short-lived neopentyl carbocation, which will undergo an alkyl shift. One of those methyl groups will slide over and fulfill that carbocation, leaving us with that compound right there. 2 methyl groups now with the plus charge carbon, then CH2, CH3. So the CH3 now on the end there was originally one of the CH3s on that quaternary carbon. Okay, so there's our alkyl shift that happens. So let's see if we can figure out what happens here. Benzene plus 1 chlorobutane with AlCl3 gives sec-butylbenzene as its major product. That's what I drew up here. Here's the hydride shift that happens. The reactive intermediate is this secondary carbocation, which gets attacked by the aromatic ring, like that, in order to make sec-butyl benzene. Here's our neopentyl. Chloride. Instead of making a neopentyl group, we now have our attachment here at the quaternary carbon. Okay, that's because we made a neopentyl carbocation. Here was the alkyl shift, right? Because carbocation next to a quaternary center, we do an alkyl shift. If it's something where I can make a very stable tertiary carbocation like this, then it could almost be a rearrangement that we could count on. Right? This neopentyl rearrangement is a famous one, so that's something we can count on. But otherwise, you want to try to avoid complicated alkyl groups, instead sticking with things that don't rearrange. Like what? Like an ethyl. Methyl, of course. An isopropyl. T-butyl. Okay. Those are all safe for Friedel-Crafts alkylation. Anything more complicated than that is prone to a rearrangement. Okay? So keep that in mind. Friedel-Crafts acylation, on the other hand, is usually a lot more useful to us. An acyl group, where I have C double bond O with an R attached, there's our acyl group. Very similar process to Friedel-Crafts alkylation. I have an acyl chloride. This one happens to be called acetyl chloride or acetyl chloride. It has that CH3C double bond O functionality to it. It is, in general, an acyl chloride. We can acylate the benzene ring with that same catalyst, with aluminum chloride. So what is it here that forms? The AlCl3 catalyst forms a resonance-stabilized acyl cation. How does that work? The chlorine attacks the aluminum. We break the carbon-chlorine bond, so we get a carbocation. So it's Rc plus double bond O. That is resonance-stabilized just by bringing one of these lone pairs from the oxygen down into the double bond, and now get a triple bonded carbon with plus on the O. So resonance stabilized carbocation. Because of that extra resonance stability right there, the acyl cation is not subject to the same type of rearrangement that normal alkyl carbocations are. So this R group can be really whatever we want. It can be branched or straight or whatever. We're just going to form this acyl cation where the benzene ring attacks the carbon and AlCl4 removes that hydrogen and re-aromatizes it. So we'll always end up with a C double bond O next to the ring, and the rest of that R group is attached to it. It has that one same limitation, like alkylation, in that acylation cannot occur on a ring that already has an electron withdrawing group to it. So if I had nitrobenzene and I tried to acylate that, RC double bond OCl with AlCl3, that's going to be no reaction. Why? That nitro group pulls electron density out of the ring, so these pi electrons are no longer available to attack the carbocation that's formed.